sure. Could be one reason behind the low attendance today. And there's a typo here. It's November 26. Okay, I'm assuming I'm audible. Somebody could confirm that. Then we can begin.
Yes, sir.
Thank you. Okay, scribes for today, ID number 143. Are you there?
Yes, sir.
144.
Yes, sir.
145. 146. 147.
Yes, sir.
148. Okay. Okay, then let's continue with our discussion on linear transformations and linear operators. Right, so just to recap what we did towards the end of the last class is, let us say T is a linear transformation between two finite dimensional spaces U and V. For any x in the domain vector space, I can write x as a linear combination of the given bases U1 to Un, and y, which is nothing but the output of this linear transformation. Since it also belongs to the vector space V, I can write y as a linear combination of the bases V1 to Vm. So as you can see, the linear transformation T gives you a relation, right, between coefficients of the bases of U and coefficients of the bases in V. That relation can be written simply as a matrix. Okay, and this particular matrix, the notation, let me once again explain here, that the subscript will stand for the basis of the domain vector space U. The superscript will stand for the basis of the codomain vector space V. Okay, so this is what is called the matrix representation of the linear transformation T with respect to the bases beta U and beta V. Okay. Is there any doubt here? Okay, so then let's proceed. This is again a new notation. Don't think I've introduced this. L of U denotes the set of all linear operators from N to U. Okay, that means if I take an element of this set, LU, that T is a linear transformation from U to U. Okay, and similarly, you also have a more general notation, UV. LUV denotes the set of all linear transformations where the domain is the vector space U and the codomain is the vector space V. Okay, so in this case, an element of this set will be a linear transformation from U to V. Okay, so compared to what we did in the previous slide, if T maps the domain vector space U to itself, right? In that case, both for the domain and codomain, we can use the same basis. Let's denote it by beta U or just beta. Okay. Then we have the same interrelationship. X, the element of the domain, can be written as a linear combination of U's. So can Y, right, which is the output of this linear operator. That also can be written as a linear combination of the same basis U1 to UN. In that case, the notation would be T beta U to beta U. Okay, this will be a matrix that will be of size n cross n and will contain elements from the field. All right, this is just a specific example of what we did in the previous slide. Is that all right?
Yes, sir.
Okay. So let's maybe take a few examples so that you understand how to obtain matrix representations of linear transformations or operators. Okay, so give me a basis of So I hope this notation is understood. P3R stands for polynomials with real coefficients with degree at most 3. Okay, so can someone give me a basis of P3R?
1x x square x cube.
And for now, let's use the same basis both for the domain and codomain. What would be this matrix? What would be the size to begin with? Anyone?
4 cross 4.
4 cross 4. Good. Okay. How will we find the first column? So if you look at this, what is this first column? The relation is TUI is summation over J from 1 to M C JI BJ. Okay, so J stands for the row index, I stands for the column index. So if I want to find the first column, I must keep I equals 1 constant, right? Which means column 1 can be found out by basically, column 1 is basically TU1, right? Represented in the basis beta. That's your first column. Right? C11, C21, C31, etc., etc. Similarly, the ith column is nothing but TUI represented in the basis of my codomain. Right? So let's follow this strategy. What would be the first column? You apply your linear transformation to which basis?
Constant 1.
1, right? The constant polynomial 1. What is the derivative of the constant polynomial?
0.
0. How do I represent 0 as a linear combination of the given basis?
All constants are 0.
All constants are 0. So what would be my first column vector?
All zeros.
All zeros. Second column vector, d by dx of the second basis, which is x. What is the derivative of x?
1.
1. The constant polynomial with constant 1. How do I write this as a linear combination of my bases?
1 0 0 0.
1 into 1 plus 0 into x plus 0 into x squared plus 0 into x cubed. So what would be the second column vector?
1 and all zeros.
1 0.
That's good. Third basis is x squared. So what is its derivative?
2x.
2x. How do I write 2x as a linear?
0 2 0
0 2 0 0.
Good. The last column would be
0 0 3 0.
0, 0, 3. Okay, so this is the matrix representation of this linear operator. So if you look at it, one advantage is if I want to, for example, implement this derivative in MATLAB, I hope all of you know, you cannot do it if you just do it directly, right? But if you know that this I'm going to apply only on polynomials of degree at most 3, and write this matrix and use this matrix to compute the derivative. For example, if I want to compute the derivative of the polynomial I don't know, 5 minus 4x plus 10x squared. Right? So what should I do? Should find the representation of this polynomial in the given basis, which is, what is the representation?
5 minus 4, 10, 0.
5 minus 4, 10, 0. And then d by dx of this polynomial p represented in the basis beta would be t beta beta, which is what we have just found, into this vector, which would be, if I just multiply this, what happens? This is 5 times the first column minus 4 times the second column plus 10 times the third column. Okay, and as you can see, all the non-zero entries are at different positions. So therefore, it would be 5, minus 8, and 30. Sorry. No, 5 times the first column, which is 0. So minus 4 times this. That would be minus 4, and here you would have 20. 0, 0. Right, and then you can expand this in the basis. So this would be minus 4 plus 20x, and which is, you can of course directly differentiate this with respect to x. Right, analytically you will get the same thing. Is it clear?
Yes, sir.
Yes.
Okay. Let's look at another example. Rotation in the xy plane. And maybe for now we can assume that the rotation is by an angle theta in the anti-clockwise direction. So again, can someone give me a choice of the basis? Any basis for R2?
Sir, one x-axis and y-axis.
X-axis and y-axis, okay.
And other can be 45-degree lines. मतलब y equals to x and y equals to minus x.
Oh, you want different bases, okay. Theta u and let's say alpha u. So y equals x, that is 1, 1. And the other one would be 1 minus 1. Is that fine?
Yes, sir.
And you want to find this r theta. The domain has basis beta u, the codomain has basis alpha u. Is that okay?
Yes.
Okay. So let's try, and of course I hope all of you agree the dimension of this matrix, the size would be 2 by 2. Right. So first task is take the first basis of my domain, which is this 1, 0. Apply this rotation transformation. So maybe let's say this is what you get. So this is 1, 0. What would be this point? What would be the x coordinate of this point after rotating the x unit vector?
Cos theta comma sin theta.
Theta, and the y coordinate would be this. So what would be the first column vector? So the idea is cos theta sin theta, you want to represent this output as some scalar times 1, 1 plus some scalar times 1 minus 1. So what would this be? Can you fill in the blanks?
cos theta plus sin theta by 2
Good.
and cos theta minus sin theta by 2.
You can check if both of these equations are satisfied or not, right? So then what is the first column vector? Cos theta minus sin theta by 2. Right. Similarly, what happens if I take the second basis? Second basis is 0, 1. So let's see, it's this vector. Maybe you get this vector after rotating by an angle theta. If this is 0, 1, what is the x and y coordinate of this point?
Minus cos theta sin theta.
Good. So how do I write minus cos theta and plus sin theta as a linear combination of 1, 1 and 1 minus?
Minus cos theta plus sin theta by 2
Minus cos theta plus sin theta by 2
minus cos theta minus sin theta by 2.
Is that okay? Then
Giving that point minus sin theta cos theta.
Yes, sir. It will be minus sin theta cos theta.
minus where? Abhi?
In representation, blue vector will point to minus sin theta cos theta.
Okay, great. Thank you. Minus sin theta and cos theta. Okay, so then how about this? This is fine? Yes. Yeah, this should be fine. Oh, then this will also be exchanged, right? Sin theta, cos theta. So what would the new scalars be?
Minus sin theta.
Cos theta minus sin theta by 2 and minus cos theta minus sin theta. That's right. Yes, I think it should be fine. Okay. So the second column vector would be cos theta minus sin theta by 2, and this would be minus cos theta minus sin theta by 2. That fine?
Yes.
Okay, a quick question. I think there was few classes ago somebody had asked this question: why is the order in the basis important? Does this answer your question? The sense, if instead of alpha u, if I choose alpha u prime to be this basis, 1 minus 1 and 1 1. So as you can see, as sets both are the same, but as bases they are different. So r theta beta u alpha u prime, what would that matrix look like?
So we need to interchange the rows.
Rows, right? Is that clear to everyone?
Yes, sir.
Okay, so you can again see that why or what is the significance of the order in the basis set. Okay. Let's take maybe one more example, or maybe. Do you want one more example, or is it okay? So in first two examples, we looked at linear operators, right? The domain and codomain vector spaces are the same. In this third example, the only difference is that the domain and codomain vector spaces are not the same. So in principle, this is a linear transformation. Should we do this, or are you guys okay with it? You want to do this? Okay, let's do it. Okay, let's call this U and this as V. We'll write it over here itself in order to save the space. So beta U, let me choose it to be your usual spaces. Beta V also, let me choose them as it is. 4, 5, 6. Okay. I don't think this much space is enough. Okay, so P is a third polynomial P0 plus P1x plus P2 x squared plus P3x cubed. Right, who would give me the first column? And what would be the size? Size of this matrix, anyone?
Sir, 4 cross 4.
No.
7 cross 4.
7 cross 4. Good. Okay. Give me the first column vector. Once again, for those who are not following, I'll just repeat. If I want to find the first column vector of this matrix, I need to apply this linear transformation to the first basis element in beta U, find the output and represent that in the chosen basis of my codomain vector space V. Okay, so the first basis of beta U is 1. What happens if I apply TP to 1? Remember, TP is defined as your usual multiplication between polynomials. So what happens if I multiply the polynomial 1 to the polynomial P? Gives me P itself, right? So how do I represent this polynomial P in the basis beta V, which I hope you can see over here?
1, 1.
No, by 1. I want to represent P in the basis
Yeah,
beta V.
P0, P1, P2, P3. And zeros.
1, 2, 3. Okay. Next, what is the second basis? Second basis is X, right? So what is P into X? Or X into P, whatever.
0,
P.
P0, P1, P2, P3, and 0, 0.
Third,
0, 0, P0.
have you seen such a matrix somewhere? Fourth column,
Communication system.
Convolution.
exactly. Right. This is sort of representing discrete convolution. Okay, so I mean, have you studied Z transform till now?
No, sir.
Okay, fine. But I hope you sort of see I mean, I hope you have seen this matrix as I guess Vandan told. All of you agree, then can sort of see that convolution is doing nothing but it is sort of representing signals as a polynomial and then multiplying the polynomials to get the output of the convolution. This is true as far as your discrete signals are defined over a finite interval of time. Okay, and have you also studied what is such a matrix called? Such a matrix, in the sense you can see every column, right, is a shifted version of the previous column. Okay, so such a matrix is called a Toeplitz matrix. That's just small deviation from our topic. Anyway, so I think I hope now it is clear what does it mean to represent a linear transformation in a given basis as a matrix. Okay. Okay, now the question we'll consider is, so we specifically look at the rotation matrix that we derived. If I change the basis, does the matrix remain the same?
No.
No. But I think the thing you should realize is the matrices are different, but they are representing still the same linear transformation. Okay. So there are two questions that we are interested in here. One is, can we find a relation between two matrices that represent the same linear transformation? Okay, so for example, in this case, alpha u has been changed to alpha u prime, the matrix has changed. And of course, here it is evident that all we have done is exchange the rows. But we also, I hope all of you remember that the matrix R theta in the basis beta u would be cos theta sine theta, and I think it's minus sine theta cos theta, right? Here you can see that the matrices do not have a very simple relationship. But is there a relationship that we can find out between all these matrices? And second, and a slightly more important question is, if I want to understand what that linear transformation is, if I want to intuitively understand via matrices, right? Now, coming up with matrices requires us to specify the basis. Okay, so then if my job is to understand what that linear transformation is doing via matrices, and in order to obtain matrices, I need to choose a basis. So what sort of basis should I choose so that whatever is the resultant matrix I get, it becomes very easy for me to understand what that linear transformation is doing. Okay, are the two questions understood?
No, sir. Can you repeat?
Sure. So we have seen that if I change the basis, the matrix for the same linear transformation changes, right? Now,
Yes.
right. So I would first of all want to figure out that if I change the basis, how is the matrix representation for the same linear transformation going to change? In the sense, what is the relationship between these two matrices? Right? Of course, if I take any 2 by 2 matrix, that will not necessarily represent the rotation in XY plane. right? So there must be a specific subset of 2 by 2 matrices that represent the rotation matrix, sorry, the rotation transformation in some basis. And vice versa, if I am given a rotation transformation and different choices of bases, I will get different matrices. But I want to actually know what is the relation between these two matrices. Okay, so given this matrix or this matrix and the bases involved, can I convert this matrix into this? So that is the first thing I would want to do. Okay, and the second thing and a more deeper understanding is, or a more deeper question is, as you can see, depending on my choice of bases, I will end up with a matrix. Right. So is there a choice of bases such that the matrix that we get, right, via that matrix, it becomes very easy for us to understand intuitively what that original linear transformation is doing. See, if I give you these two matrices, 1 and 2, which is the matrix which is easier to understand?
Second one.
Second, right? So in general, can we come up with a principle as to what sort of matrices are very easy to understand, and then how should I choose my basis so that I end up with that kind of a matrix? Okay, because whatever matrix you get, it completely depends on the choice of the basis. Okay, now are the two questions understood?
Yes.
Okay, so let's get started with the first question. Okay, so let's say I have a linear operator, okay, L of u, I mean T, which is an element of L of u. Okay, and we have seen how to compute its matrix representation in a particular basis. There's a typo here. Let's just stick to beta. Oh. Instead of beta, if I choose some different basis alpha, right? We have already seen that these two matrices can be different, right? So is answered already, but now we want to find out how are these two matrices interrelated with each other. Okay, not in terms of theory. In theory, we know these are two matrices which represent the same linear transformation, but computationally, how are these two matrices related? Okay, that is the question we are going to answer next. So let beta and alpha be two bases of the same n-dimensional vector space U, and let us say we have already found out T beta beta. Okay, now if you recollect, we did this concept of vector space isomorphism, right? So since I have an n-dimensional vector space U over the field F, automatically, right, U becomes isomorphic to the vector space Fn. Right, I don't remember the proposition, but there was this proposition where we proved that two vector spaces over the same field with the same dimension are isomorphic. Okay, and I can also specify a particular isomorphism. Okay, so n beta is an isomorphism between U and Fn, and I'm going to define it in this way. N beta maps the first basis vector of the vector space U to even n. Now what is even n? Is this vector 1 followed by n minus 1 zeros. Okay, and in general, Ekn denotes this vector of all zeros except the 1, and the 1 is in the kth position. So in some sense, again, relating this to your signals and systems, this is your discrete impulse. Okay, and this n beta maps u1 to e1n and it maps un to enn. Right? Do you see why this will be an isomorphism? I've defined the function on the basis of my domain. I'm saying n beta is going to be linear, and all it is doing is it is mapping one basis to the other basis of the other vector space. So of course we have used this in the proof of that particular proposition. Right? So can I assume all of you agree that n beta is going to be an isomorphism?
Yes.
Okay. Now what is this isomorphism giving? So if I take an arbitrary vector x in U, n beta applied to x is going to give me nothing but the representation of that vector x in the basis beta. Agreed? And this of course is going to be a column vector in Fn. And similarly for any y, n beta y is also going to give me same y beta is the representation of y in the basis beta. So this is also going to be a vector in Fn. Okay. Now similarly, if I have a different basis, right, of the same vector space, so alpha, let's say the basis contains p1 to pn elements, right? So using this alpha, I can come up with a different isomorphism. Yeah, I've already proved U is isomorphic to Fn, but that doesn't imply that there exists only one isomorphism. Right? So with the basis alpha, I can define this n alpha, which is going to be an isomorphism in an analogous way. Okay? And what that is also going to do is n alpha is going to give me nothing but the representation of the vector onto which it is applied. Sorry, so there is a typo here. This should be A. Is that clear?
Yes.
So using this, can we find the relation between T beta beta and T alpha alpha? So let us look at this particular diagram. Okay, so you are given this vector space U is, let's say for now, representing the domain of your linear transformation T, and this U represents the codomain, okay, U. If I choose a particular basis beta, then n beta is an isomorphism from U to this particular copy of Fn. Okay. Similarly, if I choose the basis alpha, then using this isomorphism n alpha, I get an isomorphism from U to this copy of Fn. Okay. Similarly, for the codomain, right? If the codomain is equipped with the basis beta, then I have this copy of Fn. If the codomain is understood to have basis alpha, I have this copy of Fn. Now, what does this matrix T beta beta do? Okay, it maps this copy of Fn to this copy of Fn. And similarly, T alpha alpha, which is unknown, right? It maps this copy of Fn to this copy of Fn. Okay, so in some sense, if you think of this as roads going from one copies of or some vector spaces to the other, as of now, this road is inaccessible because we don't know T alpha alpha. Okay, but we do know what is T beta beta. So what can we do? If I take a vector here or if I take a vehicle here, in that analogy, this vehicle should reach here. This is the destination. Source, destination, but this road is inaccessible. So what is the way out? How do I reach the destination?
Through T beta beta.
So we start here, then where do we go?
U.
U.
Then
Fn.
Then exactly. Then we know T beta beta, so this route is accessible. We can go here. Then go to this place and go here. Okay, and we want to do this computationally. So we don't want to use this route. Okay, remember the vector space U may be a vector space of functions and all that. We don't want to bring in functions. We still want to live in a world of matrices. Okay, so we should be able to go from here directly to this place here. And change the color. And how do I go from this directly here?
N alpha inverse N beta.
Exactly. So this is N alpha inverse N beta. A trivial question, why should N alpha be invertible?
Is isomorphic.
Isomorphic.
It's an isomorphism. Is N alpha going to be a matrix?
Yes, sir.
Why? Or is N alpha inverse going to be a matrix? Maybe that will give you, this is a hint. If N alpha inverse is a matrix, of course N alpha is also a matrix. But is N alpha inverse a matrix? What is N alpha inverse going to give you? Let's say N alpha, go back to white. N alpha inverse acts on what? It acts on
Fn.
in Fn. So in other words, it acts on representations of vector in the basis alpha, right? And gives you what?
U, an element in Un. U.
In U. And what element would that be? Would be the same element whose representation is acted upon, right?
Yes.
It would be X. X is in U. So can this be written as a matrix? Or is this transformation a matrix itself? See, X is the original vector from the vector space U, right? So this could be a function, for example. Right? N alpha inverse is a map from Fn to U. So this need not be a matrix, right?
Yes, sir.
But how about this? N beta, N alpha inverse. That goes from Fn to
Fn.
Fn.
Fn. And what does this give? Let's say if N beta and alpha inverse acts on the representation of X in the basis alpha, what will this give you?
X adversus beta.
Exactly. It will give the representation of the same vector X, but in the basis beta. So this, of course, is a matrix. I hope you understand that small detail here.
Yes.
Yes, sir.
Okay, so what I can do is again the same story. This route is closed. I'm going to begin here using this composition n beta composed with n alpha inverse. This thing I'm going to denote by a simpler notation, n subscript alpha to superscript beta. What this does is changes representation from alpha to beta. Okay, so using n alpha beta, I can go here. T beta beta is something that I have assumed that I know. So I can go here. Then again, another change of representation, okay, which also is known. So this again I'm going to denote by n subscript beta superscript alpha. Changes representation from beta to alpha. Okay, the destination, if this route was accessible, right, then this and this have to reach the same destination. Agree?
Yes.
Okay. So if I start with the representation of x in the basis alpha, then first I change its representation to beta. Okay, so I get x beta, which is n alpha beta, which remember is a matrix. So this I can multiply to the column vector x alpha. Then I can operate with the matrix T beta beta on x beta. What I'm going to end up with is the representation of the original vector y in the basis beta. But what I need is y represented in the basis alpha. So for that I use this change of representation n beta alpha. So to summarize, what I just spoke was this. And this must be true for each and every x, right? It cannot be true only for a particular x. So if this is true for all x, then I have in the middle over here. What should this be? And this must be a matrix. So this is, as you can see, is a matrix that takes representations of x in alpha and gives representation of y in alpha. Therefore, this matrix has to be the representation of t in alpha, or where the domain and codomain both have a basis alpha. Does that make sense?
Yes, sir.
Okay, so this is how the two matrices which represent the same linear transformation are related with each other. And of course, what is the relation between n beta alpha and n alpha beta? Right? They are inverses of each other, obviously. Okay, so just simplifying the notations, if I denote one of them, let's say n beta alpha by some matrix S, then I get this relation between the two matrices. This, I mean, when we have two matrices related in this particular way by some matrix S which is invertible, we say these two matrices are similar or related via a similarity transformation. Okay, so similar, do not think of this word as the word that we use in our day-to-day life. Similar is a technical mathematical word over here. We say two matrices are similar if they are related by this sort of a relation through some invertible matrices. Okay, so that is what is written over here. Okay, so two matrices A and B are similar if there exists an invertible matrix, say S, such that D is SAS inverse. Okay, and the transformation that takes the matrix A and gives you the matrix SAS inverse is what is called a similarity transformation of the matrix A by the invertible matrix S. Okay, so quick question here. If I have a linear operator from U to U, it's the dimension U is n. Let's say A is a matrix which represents T in some basis beta. What other matrices would also represent the same linear transformation? Can you answer that question? I'm giving you one matrix which represents this linear transformation. Right? Can you find all other matrices that represent the same linear transformation?
Sir, all other matrices will be of the form SAS inverse.
And what should S be?
N cross N matrix.
More than that? Only n cross n?
Invertible.
Invertible,
Yeah.
right? So for all S in, remember the set of all n by n matrices, you have seen that forms a group which is denoted by GLN, GLN-R, or GLN-F, let's say. Okay, SAS inverse can be understood as matrix representation of the same linear transformation T in some basis. Okay, we don't know the basis to begin with, but we can find it out. Okay, but so in principle, what that means is you may have infinitely many matrices that represent the same linear transformation. Okay, so in that sense, what I want to sort of give you as a take-home message is linear transformations or linear operators are at a different level compared to matrices. Okay, you may have only one linear transformation, but you can have infinitely many matrices in principle that represent that only single linear transformation. Does that make sense?
Yes, sir.
Okay. That's the second question that we posed, right? What matrix representation should we prefer if the goal is to intuitively understand a linear transformation or a linear operator? Right? And that question now translates into what should the basis be chosen so that it is easy to understand that linear transformation T? And you try and answer that question.
So, like it should be a set of vectors. In each vector, it should have only component in one dimension.
Basically, you're trying to say that the beta u should be such that T beta u must contain as many zeros as possible. ideally, as you said, n minus 1 zeros, right?
Yes.
Think of a 3 by 3 matrix. Okay, so let's say dimension U is 3. Okay, and let's say beta U is U1, U2, U3. And say T beta beta is 0, A1, 0, A2's, let's see, more interesting, this 8300. How do I understand what this linear transformation is doing? So given this, can you find out what is TU1?
Yes, sir.
What would that be?
The first row will become last row, and
No. I'm asking what is TU1? See, U1, U2, U3 are vectors from that vector space, right? They are not matrices. Don't think of these as matrices. What is, as I said, I want to use this matrix as a way to understand the linear transformation T. Okay, so if I apply T to U1, where this is what is given to you, can you answer this question? What is TU1?
Will
The
it be
vector in the chain of vectors.
Once again,
It is vector in chain.
which vector? Like if you look at this matrix, you should be able to answer this question. What is TU1? If this
0,
is the
0, A3.
no, TU1 is not 0083.
A1 U1 plus A2 U2 plus A3 U3.
No,
what is U3?
What are elements of
what are elements of?
U1.
U1?
So there are some vectors. I don't know. I mean, for example, this could be sine t, this could be cos t, this could be sine 2t. I mean, why is that important? I'm asking you what is TU1. So what is the answer you can give over here?
Sir, will it be A3, A1, A2, the representation
Once again?
in beta? A3, A1, A2 means it will be the representation of the matrix you will get in beta U.
No. See, TU1, did I write representation of TU1? T is a operator. So T is a transformation from U to U. So I expect you to give me a vector in U which is TU1. So what would that be? How do you think we came up with this matrix? What do we do in order to get the first column vector?
Sir, apply the transformation of first element of beta
So what is the first element of beta U?
U1.
U1. So what do you think is this? Is TU1? Is this TU1?
Yes.
Yes, sir.
No, this is not TU1. For example, TU1, I mean, think of the derivative case when the vector space was polynomials. Zero zero A3 is a element in F3, isn't it?
Yes, sir.
00A3 need not be a vector of the vector space U.
Yes, sir.
So again, answer my question. What is TU1 if I give you the first column vector here? What is TU1? Okay, let me make it more simpler. So this 00A3, what is this? This is the representation of TU1 in the basis beta.
Yes, sir.
So then what is TU1?
A3U3.
Good, thank you. That is what my question was. See, please don't get confused between the representation of a vector and the vector itself. In the same way that I hope you're not confused between the matrix representation of a linear operator or transformation and the actual linear transformation. TU2, what is TU2?
A1U1.
U1. And what is TU3?
A2U2.
A2U2. Good. Right, so you can see why we would want as many zeros as possible in the matrix representation. Compare this with if you had T beta beta to be something of this form: A11, A12, A13, A21, A31, A22, A23, A32, and A33, where none of them are zero. In that case, what would TU1 be?
U1 A11 plus U2 A21.
A11 U1 plus A21 U2 plus A31 U3, right? And similarly, TU2 would be whatever, blah, blah, blah. TU3 would be A13 U1 plus A23 U2 plus A33 U3. Which gives you a better understanding, one or two?
One.
One, right? I mean, it's very easy to understand what that linear transformation is doing. Because once again, remember, the only thing you need to understand about that linear transformation is what it does to a basis.
Yes, sir.
What if I gave you a basis beta where you have the matrix becoming something like this? What would TU1 be?
A1U1.
A1U1.
So now if I compare, let's call this 3. 1, 2, and 3, which is the easiest one?
3.
3.
Yes, sir. 3.
Why is it easier compared to 1?
Sir, because we are just scaling the corresponding terms.
Great, right? We are not mapping
U1
one
is
basis to a different basis. See, in 2, what is happening is one basis is getting mapped to a linear combination of all bases. In 1, what is happening is one basis is getting mapped to a different basis and getting scaled. In 3, one basis is getting mapped to just a scaled version of the same basis, nothing else.
So, sir, can we say that U1, U2, U3 are eigenvectors of this
Yes.
matrix T?
Yes. So this is the way I would want you to understand eigenvectors, not just as a simple numerical schema with TU1 equal to A1 U. Why that is important, I hope you realize now.
Yes,
So
sir.
this U1, U2, U3 are nothing but eigenvectors. And the conclusion here is if beta consists entirely of eigenvectors of T, then what sort of a matrix would T beta beta be?
Diagonal.
Exactly. Diagonal. And again, the motivation why we want diagonal matrix is because it helps us understand the linear transformation in a very easy way. Okay. We don't have much time. Let me see. So this is sort of a very specific case. Let us first look at the general scenario. Okay, so let us look at what is called an invariant subspace. Okay, so let T be again a linear operator, and let us say U can be written as a direct sum of two subspaces V1 and V2. All right. Now T is a linear transformation from U to U. Instead of that, assume that I am allowed to operate T only on vectors coming from subspace V1. Okay? This is what this notation means. The domain of T is restricted to the subset V1 of the original domain. Okay, and similarly T such that its domain is restricted to V2. Same. The only difference is instead of restricting the domain to V1, it is restricted to V2. All right. So I'm sort of looking at the linear transformation T on a smaller set. Okay, that is the idea behind this. Assume if, okay, this if is a pretty big if, that T maps all elements of my subspace V1 within itself. Okay, once again, this is a subset or equal to V1. And also assume that T maps all elements of the subspace V2 to itself. If, okay, I mean, don't say that how can this happen or this cannot happen. Assume that this is the case. Then in a basis, which is formed by taking union of bases of the subspace V1 and the basis of subspace V2. How will this matrix look like? So assume
Diagonal.
no. Assume dimension of V1 is K. Therefore, dimension of V2 is N minus K, because of course, should have written this. Dimension of U, I'm assuming, is A. How would this matrix look like? Let's say P is alpha 1 to alpha K, which are the bases of BV1, and alpha K plus 1 to alpha N are the bases of BVN. Oh, sorry, BV2. Right? Or if you want, I can use same notations that I've been using for the bases. Here, U1 to UK are a basis of the subspace V1, and UK plus 1 to UN, let's say, are the basis of the subspace V2. For example, so if I want to find this matrix, right, I'm of course going to do the same thing that I've been doing. What can PU1 be, given that this is true?
Sir, will the first k columns will be ik and then I of n minus k?
I'm asking you. See, I'm saying PV1 is a set, right, which contains all elements that T maps to from V1. See, I'm not saying T V1 is V1, right? I mean, this is a set. Okay, think of this as a set, not element-wise equality.
Sir, what is B over here?
B is the basis of U, right? I mean, won't it form a basis of U? I'm saying U is a direct sum of V1 and V2 subspaces. BV1 is a basis of V1, BV2 is a basis of V2. So if I take a union of these two bases, I'm going to get a union of the entire vector space U, right?
Yes.
So what can TU1 be?
Sir, some constants time U1 plus some constant time U2 up to UK.
Up
A
to
linear combination of U1 to UK.
alone, right? What about the other coefficients?
Others
They
will
will
be
be
zero.
zero.
Zero. Okay, that is important. We don't know what these A1 to AK are, but we are sure that all these coefficients have to be zero. Right? So now, can you answer this question? How would P beta beta look like? Size would of course be n by 1, n by n. First column, some,
A1 to AK.
right? So let's just put a dot. Followed by n minus k's zeros.
Zeros.
How about the second column?
Some
They,
dots.
they will also be the
Same pattern,
We
right?
can divide this matrix in 4 parts.
Great. Here we don't know. There could be zeros, there may not be zeros, right? That we don't know. We are not saying that these cannot be zero, right? All we are saying is we don't know what this can be, but we are sure that everything below these have to be zeros.
for K
This
column.
is, yes, for k columns and k rows. How about k plus 1?
Zeros.
Zeros.
Zeros. And
Some constant.
Then
some,
B1 to BK.
right.
Some of the constants.
What do you think this matrix is? Right? This part and this part.
The upper left is T beta 1 beta 1.
Right? Or this T restricted to V1. This is T restricted to V2. Okay, and such a matrix is what is called. What do you think this is called? If this matrix is called diagonal, then what should this matrix be called? Just sort of a stupid question. Don't think about it too much. If you have the answer, you can give me. Otherwise, it's okay. This is what is called a block diagonal matrix. Okay, so it is not diagonal, but if we look at it from a distance, it appears to be diagonal. But on the diagonal, you don't have only entries, you have smaller matrices. Okay, so that is what is block diagonal. Okay, and these subspaces V1 and V2 are called invariant subspaces of the linear transformation T. Okay, or in some books, it is also referred to as a T invariant subspace. Okay, so the definition is what I'll read and stop for today. Let T be a linear operator on U if V is a subspace of U such that for all elements of that subspace, right, U in capital V, TU belongs to the same subspace V. Okay, then V is said to be an invariant subspace of T. Can you quickly think of Examples. For any arbitrary linear transformation T, can you give me 2 invariant subspaces? Okay, I will not torture you more. Just give you the answer. Our vector space U, of course, is also T invariant, right? And similarly, the subspace which contains only the additive identity. Okay? These two are always going to be invariant subspace, no matter what your linear operator is. Okay, so they sort of don't give any block diagonal structure, right? So that is why they are sort of non-interesting examples, but they still satisfy the definition of invariant subspaces. Okay. Right, so we'll stop here for today, and maybe you can already imagine what is the relation between invariant subspaces and eigenvectors. Okay, because eigenvectors give you a complete diagonalization. Invariant subspaces give you a block diagonal structure. So of course they have to be related, right? So that is what we'll take up on Tuesday. Okay. So see you guys on Tuesday. I hope you found this class interesting and hope to see more of you on Tuesday. Thank you. By the way, I hope the message has been received by everyone.